It's really a pleasure to have you here. You are also an expert on the field that some of the people in the group, we are working, so we're really happy to have you here. So a few words about Ken. So he's an associate professor at the Institute for Materials Chemistry and Engineering at Kyushu University in Japan, where he has led his independent research group since 2019. He obtained his Ph.D. in 2010 from Keio University before beginning his academic career as an assistant professor at the Chemical Resources Laboratory of Tokyo Institute of Technology. So, and he has also held visiting research positions at the University of Houston, Kyoto University, and the Technical University of Munich. And he was awarded tenured Kyushu University. I guess I'm not pronouncing it correctly, but in 2023. So just a few words on his expertise. So Professor Albrecht is an expert in the design and synthesis of organic functional materials for optoelectronics and also other applications, as I think he will show. His research spans dendrimers, luminescent radicals, OLED materials, and supramolecular chemistry, with pioneering work on the development of stable tenured radicals, among others, and bright luminescent radicals. So please, Ken, the floor is yours.
Okay, thank you for the kind introduction, Núria. And today, I'm Ken Albrecht from Kyushu University, and today I want to give a seminar on this kind of title, but actually a bit more other kind of luminescent materials too. And she gave already some self-introduction, but here is also a brief self-introduction of me. Probably you can guess from my name. I come half from Germany, actually. My father is German. So I was born in Germany, but soon moved to California. And then in most of the time, I grew up in Japan. And my mother is Japanese. So I was educated in the Japanese system. I got the Ph.D., doctor in Keio University, which is one of the, I will say, best private university in Japan. And after that, I moved to Tokyo Institute of Technology. Now it's called Science Tokyo. They changed the name. I don't know that you recognize or not, but anyway. And since 2019, I moved to Kyushu in Fukuoka as an associate professor. And I don't know that everyone knows about Fukuoka or the location, Kyushu. Here is a map. I hope that you know the shape of Japan. We have 4 islands, 1, 2, and 2, 3, 4, these smaller ones. And Tokyo is here. And Fukuoka is located at the west side. And it's much more near to Korea and also China. And it was long time from the ancient time, the entrance of foreign culture, I would say. And still we have a bit different spirit, maybe. And during my career, I also had the opportunity to join the Lindau meeting, and Hope meeting is an Asian version. Do you know about Lindau meeting? I heard that there are many young scientists, young students also here. And this is actually a meeting that young scientist or student meets the Nobel laureates. And in between the lecture, I will give some advertisement of it. Yeah. Okay, so let's go to the research. And today, more than half of my talk will be related to the dendrimers. So here I have a introduction about dendrimers. I believe that everyone knows about a polymer. Polymer has a repeating unit, a monomer, and in principle, it's a one-dimensional chain-like object. But if you have a branched repeating unit, and if you add a branch to branch, you will end up with this kind of molecular structure. Actually, this is 3-dimensional, so it looks like a tree. And from a Greek word dendry, it was named dendrimers. And in Spain, I have to also talk that few months later, this paper, an US chemist, George Newcomb, also published a similar paper. And in that paper, he named this branched polymer as an arbolol, which is now a Spanish, I think, word, as a tree. But he was late, and the dendrimer word is now, I think, more popular. And Here's also a simple comparison between linear polymers and dendrimers. I don't want to go so much into detail, but usually linear polymers are synthesized by a polymerization reaction. So always it has this N number. So the molecular weight has some kind of distribution. But in the case of dendrimers, we usually synthesize it more with a multi-step organic synthesis, and also we purify them. So it has a single molecular weight, which is also similar to maybe natural protein and those kind of things. And a lot of research on that kind of direction, mimicking like protein in these kind of things, we also have done. But anyway, this molecular scaffold is very useful to understand the structure property relationship, I will say. And in my research career, most of the time I was working with dendrimers. Of course, we are synthesizing new dendrimers and looking at basic science or chemistry of it. In my former group, I was working a bit more with dendritic ligands. Sorry that the structure is small, but this dendrimer contains more CN double bond, the CIF base, so it can coordinate to metals. And if you coordinate metals, you can reduce or oxidize them to form some cluster or metal nanoparticles inside the dendrimers. And you can also look at the catalysis and those kind of stuff. And okay, I have a bit work on that. And also as a background, I was working with supramolecular chemistry, molecular recognition, or like supramolecular polymers using these dendrimers as a building block. But especially, I mean, in the last 10 years or so, I'm focusing with luminescent material, one for OLED application, sometimes for lasing, and also now I am much more focusing on luminescent radicals, not only actually with dendrimers, but also with small molecules. So first, before going in the radical, the reason why I end up with the radicals was because I was working with luminescent materials for OLEDs. So let me start with the introduction of OLED. I think that now everyone knows a bit about OLEDs, I hope. Maybe your smartphone display is already a OLED. This is still liquid crystal. And also you can buy a large TV screen of OLED or electroluminescence devices. In principle, the OLED device structure is relatively simple, I will say. It has two electrodes with few organic thin films. Think that this is the HOMO level and the LUMO level of our organic material. You can inject the hole and electron to the emitting material. It will form the excited state, the extons, and the charge recombination will emit light. The currently commercially available OLEDs are all fabricated by vacuum deposition technique, but from the early stage of organic electronics, I think one of the dream was to print the device. And actually, in the case of solar cells and FETs, a lot of demonstration is done for the solution process of printed devices. But this is because these devices are, in principle, have a single active layer with two electrodes. So it is, of course, in the solar cell you have to mix donor acceptor, but the active layer is a single layer. So it's relatively simple, easy to print. But in the case of OLEDs, to confine the extons, you usually need the multi-layer structure. And for commercialized devices, it's not only 3, maybe it can have 5 or 7 layers. And if you imagine already when you try to laminate 2 layers, you will face the problem of dissolution. And for a double layer, you can maybe solve it, but if you have more layers, this will be really a problem. But of course, now many companies in the industry, especially in China, they're trying to print the OLED, and I see some progress here. And because of the spin statistics, I mean, in a OLED, an hole and electron will be injected, and the hole also still has one single electron. And also the electron has some spin. So the extons, the excited states that are formed in an OLED will follow the spin statistics, and 1/4 will be the singlet and 3/4 will be the triplet. So if you use conventional fluorescent molecules, you can only harvest 1/4 of the extons, and the triplet extons will be thermally quenched. So at the end of 1990s, some proposed to use a room temperature phosphorescence materials, such as iridium or platinum complexes. And in this case, because intersystem crossing takes also place, you can harvest 100% extons. And actually, for green and red pixels in your smartphone, maybe, these kind of iridium complexes are reused. They are commercialized, but until now, no one could find a good blue emitter in terms of the device lifetime. So everyone was seeking for a new concept. And in 2009, Professor Adachi from Kyushu University, this is just coincidence that we're at the same university, but they proposed to use the concept of TADF, the thermally activated delayed fluorescence. This system has a very small singlet to triplet energy level gap, the delta EST. And in this kind of system, the triplets can be up converted to the singlet exton and emit light as a delayed fluorescence. And the good point of this system is that you can have a pure organic molecule that achieves this TADF. And I don't want to go too much into detail, but it's already 10 years ago. We could report the first solution processable TADF dendrimer, this kind of molecule that shows some TADF and is also solution processable. And I just want to explain why we are working with the dendrimers in the OLED field. One reason is because we don't have really the purity problem. I mean, dendrimers are much more pure compared to conventional polymers that are often used for solution processed OLEDs. I'm not against polymers, but polymers, again, have always the molecular weight distribution. The terminal structure are undefined sometimes. And also they have like a batch-to-batch reproducibility problem. But on the other hand, dendrimers are much more pure, I will say. Of course, they cannot be sublimed. This can be a limitation for the purification. But yeah, anyway, they are pure compared to polymers. The carbazoles have enough whole transporting property. In general, they are amorphous. These huge molecules don't undergo crystallization, which is necessary for OLED. And these have more twisted structures, so it can have high solubility, which is suitable for forming some ink for printing the device. The thermal stability is also excellent. These dendrimers start to degrade over 500 centigrade. And this homolumoseparation means it's a requirement to have a small delta EST, the singlet triplet gap, which means actually a donor acceptor kind of molecular structure. And I really will not explain so much detail, but after our first report, we improved the EQE, and also other groups are having even better materials now. We have demonstrated that we can print this by inkjet printing. And recently we are also working not with OLEDs, but a similar electroluminescent device that is called light-emitting electrochemical cells. And yeah, these kind of dendrimer TADF materials can be applied for printed electroluminescence devices. But this was kind of really an introduction, and I want to go today in the radicals. So again, here's the diagram of the electroluminescence. Most of the luminescent materials have a ground state singlet character. Of course, they are closed shell. So the excited state has a singlet and triplet character. And because of the spin statistics, a lot of triplets will be generated. And how to extract light from this triplet was the problem. And there's a lot of rich chemistry, physics. Playing around with this is really interesting. But anyway, this is a bit complicated situation. But in 2015, a Chinese group proposed to use a ground state doublet, which means a radical molecule, as an emitter in OLED. In this case, the diagram is much more simple. Ground state and excited state is doublet. Of course, you can think about a carted state that corresponds to the triplet in this closed shell system. But usually the carted states are much more unstable, so energetically high. So at the electrical excitation or photoexcitation process, you don't have to really consider about the carted state. But okay, the question is what kind of radical is emissive? And I believe that many people here in Barcelona knows about the luminescent radical, but let me introduce a bit. So this kind of trityl or triphenylethyl radicals reported first in 1960s are known to be emissive. The first report of the emission is probably in 1980s, I think. And in this paper, the luminescence of this radical is reported, but at the same time, they show that this compound undergoes some link closure reaction and turns to be non-emissive in a quite high, I would say, photochemical quantum yield. So at this time, this molecule was an interesting molecule, but not so useful as a material. But in 2006, again in Barcelona, I think this paper was really a big breakthrough, but they proposed to reported this kind of donor acceptor kind of luminescent molecule. And they showed that if you go to this kind of donor acceptor structure, the photostability will be really dramatically enhanced. And also the PLQI will be boosted with a quite high PLQI. And continuously here in Barcelona, they were developing a lot of luminescent radicals. But anyway, it took, again, 10 years, but the Chinese group first applied them to an OLED device in 2015. And after that report, a lot of effort was done to develop new, OLED materials, also our group, and this is Richard Friend's group. And recently, not only for OLED or other kind of applications, but a lot of work is now done as a qubit or quantum information science materials. And some are now interested in diradicals and also like excited state carted molecules. And also we are somehow meeting the metal complex or kind of a doublet or other kind of spin complexes that are luminescent. And anyway, maybe still 10 groups or so are actively working. Only 10 groups are working in this field. But this field I see that it is rapidly growing. And yeah, it took 20 years or even more after the first investigation of the luminescent radical. But now everyone, including our group, is trying to work on this system. So from our point of view, it was very natural to design this kind of carbazole dendronized luminescent radical, especially for the purpose of solution processable OLEDs. And actually now we also succeeded in synthesizing this kind of dendronized radicals. And just a few days ago, I received the referee report of this dendrimer, and now it is in revision. But at the early stage, we had some problem with the synthesis. It was a bit difficult for us. So at the first work, we focused on this kind of carbazole dendronized, one dendron substituted system. And first, I want to explain about this paper, this system. So first, here's the synthesis. When I talk about the dendrimers, everyone tells me that, okay, the structure is beautiful, but maybe the synthesis is tough and you cannot obtain so much amount. But for the carbazole dendrimers, we have a quite nice, I would say, synthetic route. We start with silyl-protected diode carbazole. The carbazole can be reacted with this, and this protecting group can be removed in one pot synthesis. We don't need purification for in between this annihilation and the protection, and we can obtain this second generation carbazole dendron. And by just repeating this reaction, we can end up with this fourth generation carbazole dendron. And okay, rapid means it takes 1 week. Of course, 1 day reaction, 1 day purification is standard, and 3 times that you can reach the fourth generation dendron. And in one batch, we can synthesize about gram, which is quite, I think, a large quantity for this organic synthesis. And yeah, which has a molecular weight of about 2,500 or so. And to attach these dendrons to the luminescent radicals, we decided to go through this diode carbazole intermediate. We can react this with the dendrons to form this precursor. These precursors are called the HDTM because this point still has the proton. This proton can be deprotonated with a base to form the anion, and the anion can be 1 electron oxidized to form the radical, which is, I mean, this procedure is established here again, I have to say. But I just want to note that these radicals are really air stable in principle and can be purified with silica gel, standard silica gel column chromatography. Here's the absorption and the emission of these radicals. And if you look at the emission, it is more clear. The original TTM radical has some bibernic structure, which means the excited and the ground state has a locally excited kind of character, a pi star character. But when you attach the carbazole dendrons or carbazoles, the emission turns to be broad. I'm not showing, but of course it has a strong solvent dependence of the emission. But interestingly, we found that when we go to the second generation to the fourth generation, the emission maxima shifts to the blue side. This is a bit unusual because if you attach a larger conjugated donor molecule in this kind of donor acceptor structure, usually the band gap will decrease and the emission and also the absorption will shift to the red, longer wavelength side. But this was not the case. Of course, I asked the student to confirm these results, but this seems to be true. And later I will discuss about the reason. And here's again a table of the photophysical parameters. As you can see, the TTM is, the PLQI is about 2%. When you attach carbazole, already the PLQI is much more boosted. About this value, I just want to note, in the first paper, in 2006, they reported 53%, I think, quantum yield, and they were measuring with a relative method. And I don't know, maybe also they had a bit difference in the purity in these things, but after our group and also other groups' measurements, I think that this simple carbazole TTM has even a higher PLQI, at least over 80% or so. So this first molecule was actually really a good molecule. And okay, but after, when we go to higher generation dendrons, the PLQI drops once, but again comes back at the fourth generation to 60%, which is relatively high. As a dendrimer chemist, we are happy to see this kind of positive generation effect. And the reason is because of the smaller non-radiative decay constant. associated with the energy gap law. I don't know that everyone is familiar with the energy gap law, but in general, if you have a longer wavelength or a smaller energy excited state, lower energy excited state, the non-radiative decay constant increases. So yeah, the emission PLQI will drop at longer wavelengths usually. So this is the opposite case. When we go to higher generation, the emission maxima shifts to the shorter wavelengths, so the non-radiative decay constant decreases. But anyway, the reason of this blue shift is still unclear. I didn't explain, and again later I will explain. But before that, we of course measure the photostability. This is the intensity of the photoluminescence under continuous irradiation with a laser. You can see that the TTM, the original molecule, decays or degrades in few seconds to few 10 seconds. But if you attach carbazole or the dendrons, even after 1 hour laser irradiation, still the emission remains. So now I can explain about the reason of the blue shift, this quite strange behavior. But before that, we actually also synthesized this kind of fragment. I mean, this carbazole kind of oligomers attached system. And in this case also, the effect is smaller, but again, we observed the emission blue shift from the 2 carbazole 3 to 4. So really, there's something behind in this kind of polycarbazole substituted TTM radicals. But I couldn't understand. So we decided to collaborate with a theoretical group from Kyoto University. And first, of course, they tried to explain it with normal kind of DFT calculations based on the static or molecular orbitals. But this really didn't help. They couldn't explain. As you can see, the beta HOMO of these molecules increase. And even the LUMO, the SOMO level also decreases. So if you just look at these static molecular orbitals, you will end up that, as usual, the higher generation has a longer wavelength emission. But this cannot explain the experimental results. So they decided to have an Hubbard model, which is a 2 energy level, 3 electron model. And in this case, the ground state has this kind of electron configuration. The TTM is a radical, and the carbazole has a closed shell. And at the excited state, 1 electron will be transferred like this. And the important parameter, U1 and U2, is the electron repulsion energy of the ground and the excited state. The electron repulsion energy is how much the orbital will be destabilized when 2 electrons are in 1 orbital. And U1 contains the ground state, so the electron repulsion origin comes from the carbazole side. I mean, the TTM side has an open shell, so there's no repulsion. And the U2 at the excited state can be mostly explained or dominated with the TTM side electron repulsion. So here are the calculated results. First, when we look at the U2, the TTM side's electron repulsion, there's no difference when we change the generation. But on the other hand, the U1, the electron repulsion on the carbazole side decreases when we go to higher generation. Smaller U1 means that this orbital will be stabilized, which results in a larger energy gap and can explain the blue shift of the emission. So to explain that blue shift, you really have to consider the electron, kind of coloration of the electrons. A bit more qualitatively, you can understand this by the molecular orbitals. The TTM side molecular orbital is always same. so the electron repulsion is same. But if we have a larger donor, like these carbazole dendrons, the repulsion when the second electron joins the molecular orbital will be smaller because the molecular orbital is more largely spread. And this is quite natural. I mean, qualitatively, you can understand this. And this is the reason of the blue shift. And a bit more, here's a diagram. The solid line is the molecular orbital, the energies of the ground and excited state without any electron-electron repulsion. Of course, the HOMO is increasing, so but the TTM side acceptor energy is same, so it will result in longer wavelengths, redshift. But if you take into account the electron-electron repulsion energy, the U1, you can see, okay, that this kind of situation is possible if you think about. And yeah, this is the reason of that blue shift. And okay, although we are still a long time struggling with the OLED application of this because we still have the instability of the device performance. But anyway, we could first publish this paper, and because of this radical system, we could really clarify or show some insights in this electron-electron repulsion, which is really interesting. In a closed shell molecule, it's difficult to quantitatively or calculate this kind of, or measure the electron-electron repulsion energy, the Hubbard U. But because these radicals have the open shell character, and at ground state, one side has full closed shell and the donor side has a closed shell. And at the excited state, the TTM side has a closed shell. And so we could discuss about this kind of Hubbard U energy in this system. So before going in the final part of the talk, just let me introduce or make advertisement about the Lindau meeting for the young students or the faculty members here. So not so many were familiar with Lindau meeting. Lindau meeting is a meeting every year held in Lindau, South Germany, near to the border of Switzerland. And it's a quite huge, I will say, meeting. 500 to 700 young scientists can meet maybe 20 to 50 Nobel laureates for a week or so. And it's really a wonderful meeting. The subject changes every year from physics, chemistry, physiology, or medicine. And also every 5 years, they have a multidisciplinary meeting. And usually in morning, they gather in this huge hall, and you can listen to 2 or 3 Nobel laureates lecture, which is also wonderful. But in afternoon, they spread in the city, and there are several lecture halls. And in each, there's a Nobel laureates lecture, and you can go to anyone that you want to listen. And in this afternoon lecture, it's a bit more smaller. So really, you will have time to give some questions. Maybe afterwards, you can talk or even go to drinking coffee or something. And it's really a wonderful gathering. And during the meeting, there are not only lectures, but also some social events. You can have dinner. Maybe you know Professor Marcus from the Marcus theory. And no one believes that, but this head is me, actually. So I could have dinner, beside him. And okay, Jean-Marie Rain. And this was a lunch from the Japanese participants with Professor Noyori, which is also famous for the chiral catalysts. And this was in the excursion, Professor Smith's. I didn't know him. He is more a biologist, but I think his lecture was the best in the Lindau meeting that I participated. And I regret that I didn't take so many photos during the meeting, but I have one slide that I want to show. This is a slide by Professor Roger Chen. I'm sad that he passed away already a couple of years ago, but he got the Nobel Prize on the research with GFP, green fluorescent proteins. He made the other color variations of GFP, so red or even blue or those kind of GFPs. And he showed a slide, some lessons for young scientists, and sometimes I look at this slide, so yeah, I want to share this. First, he wrote, okay, try to find important problems that give maximum payoff, minimum pain. Okay, he is an American. Originally, I mean, Chinese somehow, but he's American, so this is a very American, I think, way to think. But anyway, the message is really to focus on important issues or problems that you believe. Life is short, so you have to choose about your subject. Next, accept that your batting average will be low, but hopefully not zero. Batting average is a baseball word, so maybe you don't know, but it's kind of a succeeding rate in hitting the ball in baseball. So the message is, yeah, just keep trying. Your succeeding rate is not zero. And learn to make lemonade from lemons. Persistence often pays off. So even if you have some sour or not good, maybe experimental results, again, try and be persistent. And yeah, maybe you can end up with a better results or maybe good publication or something. And of course, exercise, I mean, mental health including also, that is very important. And if you get the Nobel Prize, you can say this, prizes are ultimately a matter of luck, so avoid feeling motivated or impressed by them. But there's some truth. And finally, he says, okay, find the right collaborator. I also agree with this. But anyway, I think that everyone is convinced that this Lindau meeting is a nice meeting. So if you have a chance to apply, please apply. And of course, it might be competitive, but now on the website of Lindau meeting, you can find a lot of archive of the lectures. So if you're interested, you can have a look at it. Okay, so let's go back to the research. And the last 1 or 2 topics, maybe 10 minutes are left. Yeah, less than 10 minutes. I will hurry, but I will just want to show you about really recent work from our group. And one is the CPL, the circularly polarized luminescent of the radicals. And I don't think we need an introduction, but anyway, the CPL is frequently now studied. If you have a chiral molecule, it shows some emission. And of course, some lanthanide complexes or polymers and those kind of large objects show more the G value, the difference in the left and right-handed emission. And in general, small organic molecules don't show really efficient CPL. But anyway, I think it is a worthwhile research subject. And about the TTM luminescent radicals, I again have to mention that the group here have done a very excellent work, a pioneering work. They succeeded in separating the propeller chirality of this kind of TTM radicals. But in this conventional TTM systems, the racemization barrier was relatively low. At room temperature, even it undergoes racemization. So they also developed this brominated TTM radical. In this case, the bromine atoms are a bit more larger, so it's locked, and the racemization barrier will be larger. But still, I will say the main point in these studies were the relatively low fluorescence quantum yield and also maybe the photostability. So just following the case of the TTM radicals, we decided to attach the carbazole moiety to these luminescent and chiral molecules. I am surprised that no one really did it before. This is a very easy idea. But anyway, since no one was doing, we decided to synthesize this molecule. The synthesis is not so special, but anyway, we went through the radical and we decided to attach this carbazole direct to the radical rather than going through the precursors, because sometimes the radicalization step of these brominated radicals were complicated. The emission and absorption is not, again, so special. I think this is in toluene, sorry, it's not mentioned, but it shows some CT emission around 700 nanometer. And here is the photophysical table. Again, sorry, the left is cyclohexane and right is, I think, toluene. And as you can see, the original TTBRM shows about 1% PLQI, but just attaching the carbazole boosts the PLQI above 70%, which is quite high. And we also succeeded in the chiral separation with the chiral columns. Of course, it shows the mirror image in the CD. And this is quite weak, I will say, but it shows also some mirror image in the CPL with a G value of 10 to minus 4. We want to increase, of course, maybe in the next molecular design, but at least, yeah, we could demonstrate that this molecule shows some CD and CPL with a quite high PLQI at least. And of course, the photostability was also enhanced 2 orders of magnitude or so compared to the original TTBRM. So now we can work a bit with laser. And also the racemization barrier. This is measured in 80 centigrade. So actually in room temperature, it does not undergo racemization. So we have now a stable chiral system with high PLQI around 700 nanometer near to the NIR emission. And also, thanks to the high photostability, we could work a bit with the WGM, the whispering gallery mode emission, which is not really lasing, but kind of a resonance emission from these radicals. We prepared some polystyrene spheres and doped the luminescent radicals. And when the emission wavelength matches the circumference of this sphere, and okay, the integer multiplication of this sphere, then it starts to resonate. So the original emission is broad, but you can see that already some peaks are appearing, showing the resonance in this kind of spheres. And this is one step before the lasing. And future, maybe we can show some lasing from this luminescent radical, which should be also an interesting topic. But anyway, we could publish this paper this year, and already maybe we will start some collaboration with sending these molecules. And I believe that these chiral luminescent radicals will have many applications. And again, a very short version of our recent work. We are also trying to use them for some bioimaging applications. Of course, this idea is again not only our groups. Since these luminescent radicals show emission in red to NIR region, these are promising fluorescence imaging probes for biological applications. But our idea was to use also the magnetic property, in particular also using this for MRI imaging. I again have to mention that the Spanish groups have already used them for like ESR imaging, but not really for MRI. and this fluorescence imaging. So we wanted to combine these two functions in one molecule. Here is the first generation kind of molecular design synthesized by Kosuke in my group. He designed this kind of molecule with a PEG chain. Indeed, this is water soluble, but unfortunately, we ended up with a very low, I will say, photoluminescence quantum yield. But anyway, it shows some emission in the NIR region. And also we could demonstrate that this can be used for MRI contrast agent. At least the water protons relaxation time can be enhanced when we solve this molecule. But anyway, the low PLQI was the problem. So in the second generation, we decided to synthesize this kind of molecule, which has a weaker donor. A strong CT system shifts the emission to too much red and reduces the PLQI. So we decided to have a small, weak donor. And also we decided to surround this molecule with the PEG chain because the first molecule had kind of amphiphilic structure resulting in some molecular aggregation. And in this molecule, I will not present, sorry, the detail. We don't have time. But we could really demonstrate that this can be used for fluorescence imaging and also MRI imaging. And this paper, you can see it now in the archive, and I hope that it will be published soon. So anyway, starting from the OLED and also the dendrimer systems, we are now much more working with luminescent radical small molecules, and also now with diradical, of course, the chiral system and those kind of things. And yeah, at the end, I really want to acknowledge to my group and also for a lot of pioneering work from this institute and also the Spanish groups. Because of that breakthrough, now we can have the research together with other groups. And also, this Aspire project is an international collaboration, which is funding my travel to here. So I also want to thank to this financial support. So thank you.